All right, well, this was a unit that Stanley built. It was built for a project that Mark Pocock did to study the audibility of mid-range phase distortion. And it's an all-pass filter. It's made out of quite good components. I think 1% resistors and possibly 2% capacitors. I don't know. It's got 2 channels, and you can switch in all kinds of different things. You can switch in the frequency of a second-order all-pass and a first-order all-pass, and you can change the Q. So that the first-order all-pass is always just got a Q of whatever first order is. It's not changeable. But the second order had Qs that were quite changeable. And I forget what the ultimate conclusion was, but the ultimate conclusion was that there was not really very much audibility in the mid-range phase distortion. This, for example, can be used to set up the same sort of phase response that a good loudspeaker would have if it had a Butterworth filter in it, or even a Linkwitz-Riley filter. Pocock did this stuff, you know, when he built the filter, and Stan says, no, he didn't build the filter, I built the filter. So, we damaged a microphone once here in one of its ears, and so now I don't put we don't leave the protection grid off anymore. We leave it in there. So it's just basically a entrance to the ear canal type measurement. And his name is Yorick from some Shakespearean play. And when you take off his head, which you can do, you can see that he's quite brainless inside, really. There's a story of Ewan McPherson who he was using this thing. He put a sweater on it, and it was standing here facing the door. And the caretaker came in at night, and he saw the thing in the dark, and it freaked him out because he thought it was a real person looking at him in the dark. So I think that's really quite funny, really. A few other things you can see on the lab floor. There's a few next computers here, and the monitors have failed, and last year the Next finally failed as well. We have an extra monitor, but it failed not because the computer failed, but it failed because the fan connector fell off the fan, and the hard drive overheated and probably lost its information. But the computer's probably still fine. Chris Ruhr helped us with that, and we may have some more stories to tell about that. This is a large tube that was used by a student of Stan's. I forget his name just now. He was looking at active noise reduction. So there was a loudspeaker mounted here. There's a microphone here, which is mounted in the middle of the tube. It's still there. And the other end of the tube contained an absorber system. So we were looking at, well, you can see it. If you take the camera and come over here, you'll have to move here. Then you can see up there, there's a loudspeaker. That was the noise canceller. And here at the end, if you move to the end, you'll see that there's a microphone sitting in the middle of the end. So what we would do is, there'd be a noise source sent in to the end of the pipe. It would the first microphone is sort of the reference microphone that senses what noise is coming down. You can put canceling noise down through this loudspeaker to make very little noise come out at the end. That was the idea. And we had an LMS algorithm that was working. A lot of people were working on that sort of thing at the time. We weren't the best at it, but we had a few projects doing that sort of thing. This unit here is a very sensitive pressure measuring instrument. It uses a differential pressure sensor, which is here. And in the box in there, under in all the wool, is a large stainless tank, which is the reference side. And this open side here is exposed to the noise, the low frequency noise in the lab. So we can make a recording of the signal, say for half an hour or so, and do a Fourier transform and get frequencies down to 1,000th of a hertz, things like that, which is not really acoustics, it's really weather, because by the time you go down below 0.1 hertz, the wavelength is almost the thickness of the atmosphere. So, but anyway, we found, using this, this was one of my early projects, we found that there's noise in the lab which keeps rising at lower frequencies. The spectrum keeps on going up, like 1 over f or even 1 over f squared. And so that's why when you measure loudspeakers at very low frequencies, there tend to be more noise at 30 hertz than at 100 hertz. And it's the ventilation system, and it can also be the weather, because you can't get away from this noise. It's everywhere, and it's quite interesting to have measured it like this. I'm sort of doing these things again by measuring infrasound in the cars of my friends and my own car. And this is just a recent project, and maybe I'll talk about it at the AES. I haven't talked about it yet, but have given a paper in Berlin recently, so maybe that's worth talking about. People might be interested in that. This is an old organ pipe. We use this as well in the physics of high fidelity. So when you blow it, you get a note. And then if you pull the plug out of the end, see that's closed one end and open this end. So what do you think will happen now when we do this? And so when you block it, the thing is a quarter wavelength long. When you open it, it's a half wavelength long. So the frequency between those two notes is almost a factor of 2, and it's close. Oops. Unless you seal it well, it won't go. Yeah. But so that's what we did. These organ pipes came from a friend of mine who's died too, Phil Eastman. Some people might know him, actually. He was one of our physics faculty here, and he had a whole garage full of pipe organ parts. So I could still go to one of his old garages and find pipes like that. We had quite a number of things that we used to study dithering. Let me just gather a few of them together and talk about it just a moment, if I can. See if I can find the bits. Yes, here's one of the bits. Probably still works, but we don't use it anymore. Okay, let me talk a little bit about the dithering. This was an analog devices converter, and we were able to change the number of bits on it with these switches here. It's 10 bits going from 1 to 7 on that, and then 8 to 10 here. This was the most significant bit, that was the least significant bit. And we could switch these bits and listen to the audio, and there was a variable sampling control here. It had to be wired up to power supplies, and it had BNCs for audio signals going in and out. But we could basically show what sampling theory was about. That is, it's really nice to take audio and to leave it at 10 bits, for example, take audio and then change the sampling rate. And as you change the sampling rate down from 50 kilohertz, you didn't really notice the audio was significantly impacted until the sampling rate came down to around 10 kilohertz or so. Because at that point, the Nyquist frequency would be 5 kilohertz, and anything above 5 kilohertz would be reflected back below 5. And that's where, in music, you started to get significant output. So, believe it or not, a sampling rate of 40,000 samples a second is actually quite royal. It's actually quite good. So this was used in order to show the original sampling things, and then we could change the number of bits to show the coarseness of the bits, and the fact that each time you switched out a bit, the noise level went up by 6 dB. And also, if the signal was small enough, then you could hear the distortion, because each LSB was significant relative to the signal coming through. So that was what this was used for. Then we would also add dither, and there's at the back of this thing here, there is a noise in here, so we could add noise in here. Signal went in here, came out there, so we could add the noise, and we could add noise in such a way that it would act like dither. In other words, it would be taking those coarse, least significant bits and change them in such a way that, on average, the signal would come through properly. It was Rob Wanamaker that finally did that theory completely. Stan and I worked on a fair bit of it, Stanley mostly. I did a lot of these things and so on. I think we understood it fairly well, but it was really Rob's work with his PhD that really sewed it up really well. I think, Earl, there is something here that might be of interest to you. The CD came out, of course, quite early. And we always have this rather nice CD player here that gets used. It's an old piece of Sony equipment. We just put a CD on here, and you can play it. This is the electronics. It was always interesting to show students various CDs. So we would just put a CD on here, stick a few little magnets on there to hold it on, and it will work as a CD player. And maybe I should show that, right?
Why not? Yeah.
All right, so here's our little CD player, and I'll put a CD on there, and we'll take some little magnets and we'll stick it down so that it won't do too much. And it's plugged in, so let's see if we can make it play. I need to find the play. Here we go. All right, and it's playing right now. And what's interesting is, of course, that it spins quite quickly. But as you go to higher tracks, let me do that. Let me show you what happens when you increase the number of tracks. You see, we're now going out further into track 8, 9, 10. This is a Philips test disc. And so now it's playing track 14. You can see the disc is spinning much more slowly because it's now out more, but it's going at the same linear speed on that thing. So these were the sort of things that students found interesting in the early years. But here's one of the speakers that we used. It's a buoy. It needs to be reconnected here, but the speaker had a microphone sitting there. So what we would do is the wall would be put here, and then the speaker sends a signal, and the reflection from the wall, the microphone would see that, both the direct signal and the reflection from the wall. So when you then took the steel sheet away and measured the wall, there'd be a change in the microphone signal due to the fact that the impedance of the wall was not, a really good reflecting surface like the steel. So that was an experiment. That sitting in there is a Bowers and Wilkins mid-range unit, actually, Kevlar unit. This horn is actually something that we used in the Physics of Hi-Fi course quite often. It was a very nice device. It was made by the same technician that built that electrostatic loudspeaker, Dave Sawyer, and he put it together. I said it has to be an exponential horn. And so he said, okay, and he calculated the exponential. Then he says, John, when it goes out like this, I have to make it wider to compensate for that. I said, yes, you do. So he made these calculations and did it all. It's all sewn together with copper wire and epoxy over the edge. The idea was that in the Physics of Hi-Fi course, if you just take an open driver and play sound through it, it really sounds rather tinny because the sound at the front cancels the sound at the back. And so then we would go through several stages to show how a loudspeaker worked. And the first one would be that we would just take the speaker and stick it into put it on top of a box. In fact, the box that we chose was actually a small dewar. I'll just get one, like this. So we would just take that small loudspeaker and just plunk it on here. And immediately the sound inside no longer cancels the sound outside. So immediately you get fairly wide range audio. It sounds okay. A little bit colored because of the resonances in there. But other than that, it's fine. And then to make it really even more so, we'd move to the horn. When you take the small unit, we had a very small, I remember having one which was about a little 2-inch unit from a transistor radio. It sounded horrible. But then when you held it up to here, all of a sudden the one side would be well coupled and you could face this into the class and get fairly loud sound out of a horrible little speaker like this. So it really indicated the suitability of matching the impedance to the wave as a horn does. So we typically tended to do experiments in the middle of the lab here. Now it's too cluttered with all the stuff that we put in here, but typically we would have a speaker sitting a meter away from the microphone, up at a fair height, somewhat halfway between the floor and ceiling, and there'd be absorbing material there, taking away most of the reflection from the ceiling. This absorbing material would be placed on the floor, taking away most of that reflection, so that the speaker could be measured fairly well. However, even though that stuff absorbs fairly well above a few hundred hertz, it doesn't really do anything at 100 hertz, so that the low frequencies were not measured well. So in order to measure those well, what we would do is, we would, in the maximum length sequence system here, what you'd be measuring when you measure a speaker like this is the impulse response. And we would see the impulse response would be clean for maybe 4 or 5 milliseconds before the reflections from the walls would get there. So we could gate that away And when you then took the Fourier transform of the impulse response, you'd get a good response from about 300 hertz up, maybe 500 or up. So in order to find out what the speaker was doing at the lowest frequencies, what we would typically do is take that microphone and move it right up close. Then there's very little room reflection, and we would take that data, which isn't quite correct because the diffraction from the box isn't right, but we could take that data and stitch it to the other data, and even though we don't have an anechoic chamber, we can get a fairly good idea of the response of the speaker. And to be honest, when you measure a speaker at the low end, it's going into a room which is going to have all kinds of reflections. So the necessity of knowing the accuracy of the system at the low frequencies is not all that great. And I think it really doesn't matter that much that you have an accurate measurement that's accurate to, say, a decibel at low frequencies. A couple of dB, 2 or 3 dB probably would be okay. And for normal measurements. Not very good for doing design and things like that. You really want, something a bit better, but that's what we would do. In the last number of months, we've been working on this tape recorder here that's on the ground. This tape recorder is actually a piece of vintage digital recorder from the days of the earliest digital recorders. This is Tom Stockham's recorder. Look at this. This has fallen off since the last time. It's a 16-channel recorder, and it worked very well. We wanted to get it going because we have a number of tapes, of demo tapes and maybe some early takes. This is actually the unit that shows the ADCs in it, but I won't worry about it. Too much joke, too much stuff. There were, these are the level pots, but there were, I think, 4 channels of digital audio, 16-bit digital audio. And why not show it?
Yeah, why not?
Why not show it? I'll take this away, and we can take the, I think it's still open. That's the interior guts of it. We're having trouble with some of the boards because the electrolytics are bad and some of the components have gone bad over the years. It's very difficult to keep this stuff going. But we may get it going. Even if we get 2 channels going, you can probably look at what's happening with some of the tapes and do that. So that's a project that's still waiting to go. Well, we started it, but... this is an ABX test box. Stanley and I really believe in ABX testing. ABX testing is the kind of testing in which you have 2 things that you're comparing, call them A and B, and the test box will allow you to wire up A and B and make sure that the levels and so on are exactly right. Then there's a remote head connected to the test box. This is a test box, and it has inputs for the low level and for the loudspeakers, so you can wire up almost any system. But the test box has this remote head, which has 3 buttons, A, B, and X. Now, X is either A or B. You don't know which. And you've got to find out. So what you do is you press A and X, and you see if there's a difference. Then you press B and X, and you see if there's a difference. You keep listening, and you decide. And once you've decided, you say, okay, I think it's whatever. Then you can press this button, which is test, and it tells you which it was. So you record your result. And if you do this 20 times, and you get it correct sort of 15 or 16 times out of 20, you know you're hearing something real. But if it's 11, 12 times, it's pretty much chance. And so this is a way of doing that. And then you press this button, and the computer re-randomizes what X is, and you do it again. So these ABX test boxes, I think, are really essential because, well, Stanley was always very, very insistent on such tests because you can give your body English, the way you ask questions, the way you say, oh, I like this one, I don't like that, can influence other people. And you really need to make an independent acoustic or, an audio judgment when you're testing equipment, we think. So that was the ABX box. It's been used quite a few times in the past. This is my ABX box. And I'll just show you something which shows you the silliness of things, and that is, let's see where. Yeah, there's a plug here. Okay, I'll plug it in. And as you see, it's now on this one. So let's see. I can press the button. There's no button here. I think I just have to switch it. Yes, this switch is A and B. So you had to plug the head in order to use the randomizer. Let me do that for a moment. Yes. Okay. So now we have a box here, and we had to use a randomizer. So you see, you could flip the A and B that way, right? Mm-hmm. But we had to let's see if it still works. Yes, we would. There's a little light there, and that whether that light comes on or not tells you whether that is the one you're listening to or not.
All right.
That was the way it did. But then when we wanted to re-randomize it, what we do is press this button, and let's see, how would it go? Where's the switch? It may not be working anymore. Oh yes, here's the randomize button. We press it, and it would just move the relays back and forth and leave it in an arbitrary position. So that was our randomizer. Isn't that cute? It sort of worked, but if you were really careful, you could release it and actually make it non-random. But it was an attempt to make the tests as random as we could get. It's still a good test box. It's built with nice components underneath, and we put damping material on the relays so that we could tell, because some people could tell whether the relay had flicked to A or B. This is a latching relay. Oh yeah, so this is a damping material. So yeah, no, it's very interesting how that all went. But it's still with us, and it's still a useful test box just to test things, switching. And it's quite good. The relays have low impedance, and you can wire up a couple of sets of loudspeakers to that. You seen that before, Earl?
Not that one. No, okay. No. Knew your other unit, but this one.
Yeah, you know the other one, right? Yep. This is Mark 1. Yeah. This was a project of mine years ago. I can drag it out. It was a time delay spectrometry unit, and it's got some electronics inside. It ran with a Commodore computer. The Commodore computer, there was a cable here coming out to the Commodore, and it would run a machine language program and actually make a sweep, a chirp. And so I made sine and cosine chirps, so I was able to duplicate much of what Crown was doing with Dick Heiser's original system. But I had gone one step further, and I had used not only a sine chirp, but also a cosine chirp. And if you use cosine plus I sine chirp, that's a complex exponential chirp. And so it has a direction of rotation that is either positive or negative. And when you do the spectrum, you only get positive frequencies, not both. So those that are mathematically inclined will understand that. The rest won't know what I'm talking about.